We had a very tedious day, so such is life. And I would like to invite Dr. Nitzan Barkai from Israeli Air Force aircraft industry. Please, Nitzan. כן, קצת אנרגיה.
Okay. Hello to you. I'm going to speak about the commonality between cyber warfare and electronic warfare and what we can take from it to the next generation cyber defense. And we all know about the challenges of the cyber early warning, and I'm not going to enter into it. Huge amounts of data, attacker defense asymmetry. Actually, I'm going to focus on how we handle the data diversity and dynamics, and how we handle attacks, those sophisticated attacks that involve subtle activities and involve multiple assets, which means that we need to discriminate between the legitimate activity and the cyber events, and we actually have to assess all the situation based on the aggregated picture of everything. And there are many tools and techniques to detect non-legitimate activity or normal behavior, and new tools are being developed all the time. And we are not going to replace them. We suggest an extra layer to handle the sophisticated attacks, an extra layer which will be above those tools and techniques. And the challenge in this layer is how to get the good information, the information which is relevant to the sophisticated attacks without having too many false alarms. Because the APTs, it is known that they use subtle effects, so that if we just transfer every such event to the system, it is practically cannot be handled. And it is well known from this common to all disciplines that there is a relationship between false alarm rate and probability of detection. And when we apply strict criteria, then we do not have many false positives, but we may lose some of the important information. And if we want to get all the information, then practically there are too many false alarms. We would like to be on the right green corner where the probability of detection is high enough, but with not so much false alarm. Now, we come from the disciplines of electronic warfare. Electronic warfare is, in a sense, similar to cyber warfare in the sense that it does not use any bombs or explosives, but rather it exploits signals, interceptions of signals like in the SIGINT systems or in the electronic attack systems, the transmission of signals in order to jam other systems or to deceive them, communication and C4I and so on. So cyber warfare can be considered as some kind of a member in this family, both from the intelligence aspect and from the situation awareness aspect. And actually, if we look into more details into this analogy, I'm not going to go through all the details here, but the missions are different because cyber warfare deals with IT and operational SCADA networks, business, and so on, while electronic warfare deals with air situation pictures or guiding missiles. But you can compare the intelligence efforts, hacking, to SIGINT. You can compare the attacks, text types. For example, DDoS, the denial of service, is in principle like spoofing or noise in the physical systems or in radars, which means that it is a simple kind of attack, and you can overcome it if you have enough resources to overcome it. And there are other attack types of deception, like decepting a missile and stealing it so that it does not hit its target, in principle is similar to the identity theft and the phishing and so on. And even if you compare the countermeasures, you can see that firewalls and the intrusion prevention system, so on, are in principle like the filters, guards, and all measures that are used in order to prevent interference signals from entering a system and just filtering just the legitimate signals. Now, remember that the left column electronic warfare is in the world for over 70 years. So there is still things to learn from the electronic warfare to the cyber warfare. And if I'm moving now to the challenges, let's take an example from the physical scenario of persistent surveillance, where you're looking at a certain area and you'd like to track a multitude of entities, many entities of various types, all dynamic, and we use different types of sensors, radars, optics, SIGINTs, where each sensors and each source of information provides the information in its own manner, in its own aspect. Some of them see only part of the picture, and in cases, some of them see there can be overlapping report, and then you should know that the overlapping reports belong to the same incident and the same entity, and they are not different things. And of course, the challenge of discrimination between the good guys and the bad guys, where the threats themselves try to avoid interception by hiding or behaving like the legitimate entities. Now, if you look at this picture, which is a physical scenario, and look again at the eyes of a cyber scenario, then challenges are similar: the quantity, variability, dynamics, integration of sensor, discrimination of the malicious actors. And if the challenges are similar, then we may look also in the solution and see that if there are more solutions that are similar and can be taken to the cyber warfare. And I'm going to introduce one of these solutions. This is the multi-hypothesis tracking. We use it, first of all, for cyber situation awareness, and situation awareness for itself is a notion which is a better concept than just stating alert. We know it from the physical space as well. A fighter pilot gets a full situation awareness of all the threats that can potentially be around him, and not just an alert, an immediate alert when it happens. And the same it can be applied to cyber. And I'm going to explain in the next slide about what is multi-hypothesis, what is tracking, and what do we mean by cyber multi-hypothesis tracking. The multi-hypothesis analysis, this is an algorithm methodology, non-algorithm methodology, to handle the uncertainty caused by complex and dynamic data, especially when the data is collected with various sources and the information is partial or ambiguous, and while it is streaming, meaning that we do not have the ability to wait until we collect all the data and then get a decision, but we have to decide upon the data which is streaming and that we have now, and everything is dynamically changing. Again, in the physical situation awareness, we use it, for example, for air situation pictures where there are hundreds of aircrafts in the air and all of them are moving, and one radar reports about a certain target, and then another one says that there is another one in another direction, and you ask yourself whether they are the same one or two others. You have two hypotheses and so on. And with each new report, there are new hypotheses. All of them are analyzed, being scored, and only the best, the hypothesis with the best scoring is reported to the operators, but the system keeps more of them inside. We do it also for SIGINT electronic order of battle, not just for physical platforms. It is applicable to cyber situation awareness to integrate the various sources and to support the decision making. And tracking is the process of associating the events. The obvious example is physical tracks, or tracks that you use for W and SIGINT. Tracking enables to get verification of the data consistency, to identify the past of the track, and to get some hints and prediction about the future, possible future evolution of the track. And again, if we look at it as cyber incident tracks, then the verification of data consistency can provide us with the elimination of the false positives. Looking at the past can give some clues, maybe, hopefully, to the attribution of the events. And predicting the future is a kind of a way to get more reliable threat alert from the cyber training. So if we combine both of them together, the multi-hypothesis and the tracking, we get multi-hypothesis tracking, where the distinct events that can be distinct by different types of fields. They can be different by time, by the location where they have been detected, by the sensor that has reported about them, by the type of them. For example, an event of a malicious file is another type from an illegitimate login, and they can happen in different locations, but maybe they are altogether linked somehow to some sophisticated attack. And I'm not going to enter into the details of how the hypotheses are managed, just to say that each new event is checked against all the hypotheses, and this is actually a way of keeping the history in some efficient way, because ideally each new report should be correlated with every knowledge that we have from the past. But this is too much to do when the data is streaming. But the other option is not to look at all at the past and treat every data when it comes. This way of keeping hypotheses and tracks is an efficient way. When data is streaming, we have to compare only to few hypotheses, and all the algorithms, how we keep the hypotheses to be few or even a larger number, but not an infinite number. This is some of the methodology, how to cluster and prune them, and so on. And another emphasis is the association on a time scale. Time can be played backward or forward, actually. If you play the time backward, looking at all the events, then you confirm the information consistency. It's very well for verification of the events, investigate overlooked or dropped events, and look for the actor behavior. If you move it forward, then you may predict the expected information, guide efforts of the system to monitor events in suspicious path, and try to predict and project the situation of evolution in order to have better assessment of possible impact. And actually, if we combine the backward and the forward evolution, this may generate more reliable alerts. Actually, we use the approach which we call track before detect, which means that you get the data and you try to track the events even before making the decision whether they are important or not. And only if an hypothesis track is consistent with high scoring and so on, only then you report detection. And this is the way that although you use in the sensors and in the sources of information relaxed criteria for reporting, you take all this data, use the multi-hypothesis tracking, and this is the way that you move to the happy corner of less false positives, although you've started with a lot of data. And there is another advantage that when you report a detection in this way, then immediately you can report the whole track picture, all the associated events, the possible actor attribution, estimated future impact. So the incident response can be much improved in this way. And of course, to get a full picture, we need to monitor not only the activity, but also all the intelligence sources context of the organization, intelligence taken from all the possible sources, from Rabin, from Docker, from everywhere. And they are used in, they are also sources of information, and they are used also as a way to adapt the scoring and to judge events using adapted criteria based on the intelligence. All of this is still under research because on the optimal scoring and how to make it more and more efficient. And I will just finish by showing the diagram of the next, how we see the next generation cyber situation awareness. First of all, the system should take the information from everywhere possible, for all the information and data sources, activity, context, intelligence, and so on. The information is heterogeneous. Some of it is structured, some of it is just free text, like Anonymous gave a message in the BBC and something like this. And everything should be combined. We prefer using ontology based on cyber defense models in order to use it as a common language to all the data. Ontology is not just a common language, it's also a way of arranging the data so that it reveals the relationship and the tracks between the entities. Above it, the analytics layer, the multi-hypothesis tracking, and the analytic engines are actually all over. One can use the known analytic engines, those that are rule-based engines or anomaly engines, but there are also newer engines based on the ontology and the MHT, because this structure reveals relationships between events and possible places where in the network or in a service that can be affected from such an event. And when these tracks and paths get their scoring by the MHT, then this is another kind of analytic engine. And of course, at the end, the incident response workflow, which would be interactive with human operators, but they will have much more information in order to deal with the situation. Thank you.